Introduction. My name is Tiens Henning. I'm an associate professor at the University of Auckland in a part-time position, and I also do some international work, focusing mostly in the areas of infrastructure investment. And then lately I have done quite a bit of work in the area of climate resilient applications in the infrastructure area. So it was really an honor when the TRL has asked me to be a co-author of the new Road Note 31. That was special because when I was a student, I was studying pavement design, and we had Road Note 31 as a prescribed textbook to us. So today in my presentation, I'm going to talk a little bit general first, just to give you the context on climate resilience. A little bit looking at Bangladesh, an area that you would be very familiar with. And then I will, at the end of the presentation, get to the specific chapters within the Road Note 31 that I have been helping with. So starting off, something that you're well aware of is the vulnerability of Bangladesh as a country to climate change. This is due to the location where Bangladesh is located, but also some characteristics in terms of especially the topography of your country. Depending on the literature that you look at, Bangladesh is always listed in the top 10 most vulnerable countries in the world. Most publications rate you as fourth most vulnerable, some seventh. Nevertheless, I think that you all understand the dire need for building up resilience within your country to protect people, but also then to help your economy, because with the losses that you are experiencing, there's huge economic input into the losses that you have. For the road network in particular, the areas of interest obviously is the water, and then also the extreme heat events that you get in your country. So what the climate then impact on your road network is really a combination of a number of factors. Now, I've got sympathy for you because certainly Bangladesh as a country is one of the worst places in the world to try and build a road pavement, just given your geology that you have. But I admire your innovation, and I understand there's a large length of your network that's been built with clay bricks, just to get some decent aggregates in your pavements. So your starting point with your geology is not very strong. And then something that we all suffer with as a result of maybe the economy, maybe it's factors of the geology, but often have an issue with poor construction quality also. And then extreme heavy vehicle loading. There's still a huge amount of your freight transport that occurs on the roads, and with the vehicles being overloaded, obviously that damage the pavements even more. So when we look at the climate impacts on the road network itself, the things that we are concerned about would be floods. Just a pure force of floods can sometimes wash away parts of our pavement or damage the road. Increased moisture that will accelerate the deterioration of your roads, and then the extreme heat events that certainly doesn't help with the asphaltic surfaces in particular. So despite all of these challenges, if we look a little bit back at how your road network has been performing compared to some of your neighbors, and I've got this out of the World Economy Forum, this picture, we can see that Bangladesh has held the condition of the road network intact, and then sort of since the 1916s, there was actually a slight improvement on your road network. So given all these factors that I've mentioned, I just want to acknowledge the effort that you guys have put in on your road network. We see that some of your neighbours, Thailand in particular, their road network's condition has deteriorated quite significantly, and that's really difficult when it comes to climate change. The concern about the road condition is twofold. Is number one, there's the obvious damage to our vehicles, safety, road safety, and those sort of issues that we want to combat. So it's important to have a good quality road if you want to address those issues. But also the condition of the road will impact its vulnerability to climate impacts, or some also use the term fragility. So I will get back to that concept in some of the following slides. One of the particular areas of concern that was covered by my section within the guideline is increasing heat events. Now, if we look at where we're at today, Bangladesh has already started to experience an increase in heat events, increased radiation from the sun. And certainly when whatever forecast you're looking at for climate change, that situation is just going to get worse. So the problem with the extreme heat events mainly impacts on the roads, your asphalt roads and any roads that's built with bituminous bitumen. You will find that the heat makes the bitumen a little bit softer, and it is then prone to accelerated deterioration. And also the sun, the oxidation and the sun combination creates the surface to become quite brittle. Then it is prone to cracking, and when cracking happens, then of course we get that water going into the pavement. So heat events is of major concern, and we've included a chapter dealing with climate resilient surfaces, in particularly for areas such as Bangladesh. So let's look at a few principles in the climate resilience area. And I think this figure is fundamental, and if you understand this figure, I think that you will also understand the importance for having more resilient infrastructure, not only the surfaces. There's also a chapter in the Road Note 31 about the pavement and the drainage arrangements that I encourage you to look at. It is a fantastic chapter. I've already started using that in my teaching. This is the functionality loss curve that you will find in most resilience publications. On the vertical axis, we've got the functionality, so that would be things like the rideability of your road network, the accessibility to users on your road network. And what we have is the infrastructure could be at a different starting point in terms of its condition. But then with a shock event, and this is mostly related to a weather event, you're going to get damage to that infrastructure and loss of function. What is always thought of as the major point in resilience is this ability to recover, and you will have a lot of experience of having to recover from disasters, the rebuild process. Now there's two elements that we measure. The first one is the time for recovery, and then of course the more damage there would be, the more cost you will incur. So we've got two curves here, curve A and curve B. Curve B starts at a very low current functionality, so that would be an old aging network with a lot of defects in it. And we see when a disastrous event or a weather event impacts, the damage loss will be great, and as a consequence the time for recovery will be long and also quite expensive. However, if we've got a well-maintained network, or even a network with some resilience improvements, then our damages is going to be so much less, and our time to recovery is also going to be very much quicker. So there's two messages in this graph. Is number one, a well-maintained road network is already by nature more resilient. And point number two is if I improve the resilience just even slightly, I'm going to have a huge return on investment in terms of the damage loss that I incur during a natural event. This curve is applicable to shock events. The other thing that we're also quite concerned about are those slow burning changes, heat building up over time, moisture levels increasing, and obviously they help with the acceleration of our the deterioration of our roads. And it is also a factor that would put the resilience, the starting point of our infrastructure, a little bit down the scale of functionality. So it becomes a little bit more fragile to weather events, and that's something that we want to prevent. Looking at the same concepts in terms of life cycle approach, what we have here is a condition. In this case, we're looking at roughness. So a new road will have a good roughness and a low value, and as the road deteriorates, your roughness increases. Now that increase in roughness happens on all the roads with time and then also with the traffic volume. So we expect the roads to get rougher over time, and that's the nature of how they perform. At a point in time when the roughness increase a lot, we have to intervene, and we can intervene earlier, say with just resurfacing, or if we leave the road, it may become so rough that you have to rebuild. With the impacts of climate change and getting back to those slow burning changes, increasing heat, increasing moisture, we know that the pavements will deteriorate much faster. So in terms of this intervention point, we got to start intervening much earlier than we used to. And that has a tremendous impact on our overall road maintenance budget. So it decreases in its life expectancy. When we start then looking at the resilience materials, what we try to do is extend the life of our infrastructure, our surfaces, and therefore our time for intervention is later, and the savings on the network is certainly from reduced maintenance. So having resilience in our material, in our construction quality, and also in our design is definitely worthwhile just from a life cycle cost perspective. So those are some of the principles. And now looking a little bit just closer at the topic at hand, when we start looking at the function of the road surfaces in the context of the overall pavement. So what we try to do, and in particular with the materials that you have, your clayey materials, is we want to have our road pavement as dry as possible. And there are different things that we can try and do in terms of our pavement design. As you can see here, the pavement was raised a little bit, but let's look where the water comes from. We get the side of the road where the water penetrates through the shoulders and through the profile of the road. And that is why we really encourage road designers to include a sealed shoulder, is to prevent that water from coming in through the shoulders of the road. We also expect the water to come up from the bottom, and in particular with Bangladesh in low-lying areas, we know there's a lot of the water table is quite shallow, and therefore we expect a lot of water coming in from the bottom. And as I said before, the only way to counter that would be to raise your pavement profile higher up, and I think that's some of the things you do already. The other area where water goes through the surface is into the pavement, of course, is through the surfaces. We have done some research in New Zealand, and to a large extent that we can expect all surfaces to let water go through. Obviously, the thicker asphalt surfaces are far more waterproof than a thin surface dressing or a chip seal. That's common technology here in New Zealand. I'm not too sure what extent of network in Bangladesh would have the thin chip seal or spray seal surfaces. They do let water in quite intensively. That water increase or a water filtration into the pavement obviously increases over time when the condition of the surface is deteriorating. When that surface starts losing aggregates, when the surface starts cracking, and certainly when the surface starts having potholes, a lot of water then goes into your base of your pavement and your underlying areas, and we will see that deterioration speeds up very quickly once that surface waterproofness is compromised. So in terms of the overall principle for resilient roads, we have to try and keep that water out of the pavement, and the first thing to do is keep that surface as watertight as we can. So just a little bit what you can expect to see in Road Note 31. There's a whole section on bituminous bound materials. And this covers the existing materials, so most of that has remained in the guideline. We do look at some improved materials, your particular asphalt mixes such as your stone mastic asphalt. We also look at improved practices, how we can use surfaces to be more rut resistant and also more durable surfaces. And with the durable surfaces, we have covered the areas such as your rubber additions or your additives into your bitumen to make it last longer. However, for the situation in Bangladesh, I think the climate resilient options, and in particular the epoxy modified asphalts, chip seals and cope seals, that would be of primary interest for Bangladesh. And I'm going to talk a little bit more about that technology. So the addition of epoxy in bitumen is not a new technology. We have found some literature that indicated Shell has started developing this back in the 1960s. Originally, they had the idea to use it on airfields, and certainly most of the application was on bridge decks where you've got either a steel bridge deck or even a concrete bridge deck with a bituminous surface on top of it. You need a very robust asphalt surface, and they have started using the epoxy bitumen. A good example of that is that wonderful bridge in San Francisco, and that has survived more than 40 years using this epoxy surfaces. The way that you prepare this is you've got two parts to it. Part A is the epoxy resin, and then part B is the fatty acid or the curing agent that we often refer to. And we typically use that in a 70 penetration grade bitumen. So the innovation, I guess, in the later years, starting with the OECD study of which New Zealand was part of, started looking at adding a little bit less epoxy into the asphalt so that you still get the benefits of the epoxy, but it doesn't cost you as much as it would cost for adding a lot of bitumen epoxy into the surface. So it certainly has become a little bit more viable to use where appropriate on networks. I just want to stress at this point that this technology is a bit more expensive, and therefore we want to choose carefully on which part of our networks it makes economic sense to use this technology. A little bit about the research that we've done and some of the learnings that we've done. In New Zealand, we've started looking at this manufacturing the porous asphalt mixes. So as many of you know, the porous asphalt is used on the motorways where we want the traffic to be a little bit quieter. And then also in rain events, what you do is you build or construct this porous asphalt on top of a hot mix asphalt. And what happens when it rains is the water goes through onto the asphalt and then out by the side of the road. That increases your skid resistance for your vehicles, but also reduces the water spray behind vehicles. The test that we've done mixing in the epoxy mix into the bitumen is the Cantabro test. That test is basically a drum that spins around. You add the sample, the bitumen sample, into the drum, and you add a few steel balls. And then as the drum spins, those steel balls knock the asphalt sample. And what we then measure is the weight loss between the original sample and once you have given it a few rotations in that Cantabro experiment. We're going to look at some of these results in coming slides. I'm going to jump to the figure here on the bottom right-hand side. And another technology that we have developed in New Zealand was to add bitumen to our spray seals. And with exactly the same reason why you would be considering that, and that is to have a surface that's a little bit more climate resilience and also slow down the oxygen of the bitumen. So we have done the spray seals, and there's minor modifications needed to the spray truck, and we can talk about that in coming slides also. The process of manufacturing this is not that sophisticated. Basically, in all the traditional asphalt plants or even during experimentation, I'm conscious of the fact that some of the mixing in Bangladesh takes place by manual means. So what you do is when you do the original bitumen mixing, you add part A, and then right at the end of the process, just before you do the construction, you add the agent that's going to cause the reaction and the epoxy bitumen to set very quickly. Another thing of construction to note that's important is you need to keep your equipment that you use clean because epoxy is very difficult to get off those equipment. So just be aware of that. Some of the results that I will show was done in our Canterbury Accelerated Pavement Testing Facility. So what we have here is we've got basically a bath, a circular bath. We then construct a pavement into it and then add the surface on top of it. We then test it with this loading arrangement. So both of these arms got two wheel loads on it, and we can simulate quite high wheel loads with it. So with this machine testing the pavement, we can speed up the deterioration, and a life of say 25 years to 30 years can be simulated in a short time, 4 to 6 months, depending on the situation. So we have tested the epoxy products in this captive facility, and I will show you some of the results in the coming slides. So the first one is the abrasion test. So that's a Cantabro test that I have been referring to. We have looked at different percentage mixes into the bitumen, into the porous asphalt, and then we've tested it, and the results are shown on the left-hand side. I just want to go through these percentages to make it clear what it actually means. So the first one there is the control, so that's your standard hot mix asphalts. The next one is our polymer modified bitumens, 4% addition, and then we've got the two epoxy mixes. 25% epoxy mix doesn't mean that's 25% epoxy in the entire bitumen mix. Basically, when you buy the product from the supplier, they provide it for you within a bitumen mix. And then this percentage is the epoxy bitumen component to the overall bitumen content. So in terms of the real epoxy quantity in this, it's much lower. I'll just make you aware of that in the guideline, and when we get to the specification, it's quite clear on what these percentages means. So we've tested that for two additions. One is 100% epoxy, so that's the technology that's used on bridge decks. And then we've got the 25%, which we advise our users to use on asphalts on the road, the typical road application. Now, as expected, when you look at the percentage loss in that Cantabro, my control and the polymer bitumen didn't perform that well, and those samples didn't last that long, but quite a tremendous improvement when you start adding the epoxy into the asphalt mix. Looking at the results from the accelerated pavement testing, and in this result we really try to understand the rut depth, so that is just a deformation that happens on the surface as a result of those wheel loads. And we can see that, as we expected, and we know the normal practice is that there is a bit of initial densification. So that is just a bit of more compaction that happens, and we know that that happens on all roads. So getting up to a 2.5 millimeter rut depth as a starting point is not uncommon. What we then see is the epoxy parts or sections that was built with the epoxy surface didn't experience any further rutting, whereas the bitumen, the traditional asphalt mixes, started to rut quite quickly. Just give you a little bit of information on another parallel study to the Road Note 31 document rewriting. It's also HVT program, so it's been sponsored by the same program from UK Aid. And this one really investigated the climate resilient technologies for high volume roads. This study was conducted by the University of Birmingham. We from the University of Auckland participated in that, and we also got the university in Malaysia that brought some of the fiber technology into this research. The aim of this research was to demonstrate the technical and economic sustainability of these practices. And then also we looked at a different range of traffic and environmental conditions. The study area for this one was in Ethiopia, a very hot country in Africa, so quite harsh conditions. And the study was really ultimately looking at the components that's shown there as a summary. The first one is understanding how roads deteriorates as we use this technology. That results is then looked at in the life cycle modeling using the World Bank HDM models or the highway design and maintenance models. And then we also looked at constructing some trials in Ethiopia to make sure that this technology can be adopted in developing countries such as Ethiopia. This study is almost completed now. I think there's still some work in the trials construction, but most of the other work has been completed. So just to understand the models that we use in HDM, we've got the cracking model, we've got raveling, potholes, rutting and roughness, and we also got a texture loss model. So these models run as a function of the pavement structure, condition and age, and then of course the traffic volume that you use on that particular road network. We see there's an interaction between these models, and it makes sense what we have spoken about before. The moment that you've got a lot of cracking on my pavements, we're going to see a lot more potholes coming through. We're going to see rutting increases, and ultimately, we're also going to see the roughness deteriorate much faster. I have highlighted these blocks because these blocks are the ones that we address through the epoxy surfacing technology. But as you can expect, that's going to have a net impact on both your rutting and your roughness. We have then used the trials, the accelerated testing and also the lab testing to come up with new deterioration models for the World Bank HDM models. And what you see here are the three main performance characteristics. The top one is cracking, then roughness, and then rutting. On the left-hand side, we've got our traditional asphalts, and you can see the type of pavement that we model this on. So it's a relatively strong pavement, quite high traffic. And then you can see the impact of using asphalt that's got a bit of addition of epoxy in it. So it lasts far more and far greater, but also keep in mind that the fact that it doesn't get softer in the hot climate, and also that it doesn't oxidize so quickly, give you even more benefits than just reflecting in these models. So through that study, we've come up with some recommended calibration coefficients for the HDM users, but we also encourage them to put down real trials in their country to see what the difference in performance is. So for example, we do know that pavements in Bangladesh would be deteriorating much faster than pavements in Ethiopia. That's mainly in a more moderate climate and certainly with far better materials compared to Bangladesh. What I would like to do next is just go through the sections and highlight some of the things in the new Road Note 31. The first one that we are looking at is the climate resilient surfaces, section 6.9. What the document starts off with are some general guidance in terms of providing for climate impacts on the road surfaces. So what we have are the impact of climate on the road surfaces, what characteristics is required in the surface to try and prevent those impacts, and then the typical technologies that we can look at to help. This is just an example. The list in the actual document is far more intensive. So for your application in Bangladesh, I'm going to look at the bottom two there, which is first of all to make sure that we've got less permeable surfaces and make sure that the water stays out. So the technology is standard closely or dense graded asphalt mixtures. Instead of chip seals, maybe look at a cape seal, and then you can use some of the crack resistant surfaces, and here the polymer surfaces is a particular option to look at. Perhaps not for Bangladesh so much, because you've not only got the problem with cracking, but you also got the heat problem. So for Bangladesh, I think you would be looking at temperature resistant surfaces. That's also going to give you the benefit of lower crack properties and also longer life. So we can use it in the chip seals, as I mentioned before, or we can use it in our asphalt mixes. The document and this chapter in particular also give you the design standards. So this is the typical asphalt mix properties. So it's fairly standard. You look at around a 5% air voids that you're aiming for, 6.7% binder content. Your penetration grade bitumen you use is less of an issue here, because ultimately with your epoxy addition, your bitumen will be quite hard. We also got to make sure that the minimum epoxy modified content is adhering to the indirect tensile test, or the 4-point bending stiffness test, to make sure that you reach the appropriate percentiles. But the standard percentiles are also reflected in the document. When we look at the epoxy chip seals or the spray seals, we use the same design procedures as for conventional seals, and we reference the road note applicable for that. And then also a specific guideline is provided for the open graded or the porous asphalt application. The next section that I was responsible for would be the economic considerations. Now, this is overall for road pavements. It's not just referring to the climate resilient surfaces, but I think the economic considerations becomes far more important now when you start considering alternative surfaces. And this figure will explain that. So with our economic considerations, we want to know the investment that we build new pavements for, or we want to know when we do rehabilitations or resurfacing, what technology we should use. And some of you may be quite familiar with this process, but we do the life cycle cost analysis by looking at all the future costs, and we discount it to today's monetary value. In this particular chapter, I have gone through the life cycle cost analysis, discussed the benefits in particular that we need to look at. I then look at some of the analysis tools, specific economic analysis tools that you can use in your decision criteria, and covered when you will use which one of those tools. And then ultimately, there's also multi-criteria analysis for when you want to look at factors that's perhaps outside of just economic terms. So for example, in Bangladesh, you are going to consider factors such as your community, the accessibility of the road, and those factors in addition to the considerations of economic nature. The next section that I have been also written up for Road Note 31 is the carbon footprint of road pavements. Now, as with many other countries in Southeast Asia and those places, Bangladesh is also looking at ways to reduce the carbon footprint of pavements, and also reduce your carbon emissions from vehicles. So this chapter looks at only the carbon footprint from our construction and maintenance processes. We often refer to that part as embodied carbon. So this is the carbon emissions that's associated with building something, the material you use, the transportation of my material to the site, my site construction, and energy use during construction. So as many of you may be quite aware, is that carbon emissions calculation is quite well adopted when we look at new pavements. But what we see these days is that we get far greater focus on embodied carbon during the operation and maintenance and the end of life of our road sections. So the calculations and the concepts are explained in this new chapter. I can also mention that the World Bank HDM tool is currently in revision, and I know that the TRL and HVT program is part of that. So in that revision, carbon calculations is also going to be included in the future economic analysis. To give you a little bit of a feel for the numbers, I have included some background principles. The introduction to the type of carbon emissions that you get, and then cover some carbon footprint calculation tools. This is a typical output that you're going to get on doing these type of analysis. This particular one was contributed from our colleagues in Norway and in Sweden in particular, where they have looked at different types of asphalt, compare that to concrete, and then also looked at the older type vehicles and the later newer type vehicles. It is quite clear that the bulk of emissions is within that grey bar, and that would come from the tailpipe emissions. So that's my vehicles and using the roads. Then we get to the orange bit, which is the maintenance component of my life cycle. And then the blue bit is the construction of my road. And you can see in many cases that the maintenance, so that's things like resurfacing and rehabilitation, has a far higher carbon footprint associated with it than the initial construction. So definitely something to consider and something to be worthwhile. Now, since we're on the topic of the epoxy modified binder, you will see that the initial construction and embodied carbon with epoxy is slightly higher than traditional, but you get significant benefits in the life cycle. And also the difference between concrete roads and asphalt roads is quite clear, and that research has been found right across the world. When we can just quickly look at the vehicle emissions, something also to remember is the condition of the road, and the rolling resistance is a huge contributor to how much emissions is going to come from vehicles. So as a road agency, we do have a responsibility on trying to get our roads well maintained and using the type of material that's going to reduce carbon emissions. So that is my introduction for today. Again, thank you very, very much for the opportunity. I wish I could have been in Bangladesh. That was certainly my wish, but my personal circumstances didn't allow for it. And in addition to that, we had major floods in Auckland. So flying out of Auckland was a problem in the past week, so it wouldn't have happened anyway. Nevertheless, it's still a privilege to be part of this, and I'm looking forward to the next session that's going to be on the questions on this. I just want to also acknowledge the sponsor of the project, UK8, and in particular the High Volume and Transport Applied Research Program, also our peer reviewers and our steering group for their assistance in making sure that these chapters are the best they can be for your use. All the best, and again, thank you. I can talk, thank you. Although at this stage I don't get any sound from Bangladesh. You perhaps indicate that you can hear me? Okay, fantastic. So with the lack of sound coming from your end, I'm more than happy to answer questions. Perhaps, Nigel, if you can put it for me in the chat box, I would appreciate it.
Can I talk? So can I talk right now?
Yes, yes, now I can hear you. Perfect, thank you.
Okay, maybe we can start shooting any question.
And he actually hears.
What the sound output? Yes.
So I can ask a question now.
Just sound output.
No, I think they are trying to sort, but if we can't hear in the chat, that was here.
And if there is any question.
Yeah, but we'll wait for sound out. Wait for me.
Which of the pieces?
Going
Let them try to sound out.
I can hear at this point, thank you.
Sound paper at the port. Port to এটা না আমি যখন ইউটিউব পেপার এটা ছাড়া আমি জাস্ট ল্যাপটপে যে সাউন্ড আসবে হ্যাঁ ল্যাপটপে যে সাউন্ড আমি ক্লিক করে ছাড়া ইউটিউবে ক্লিক করে সাউন্ড সেটা আসবে এমনিতে তো এখনই তো হয় আচ্ছা এখন কথা বলতে হবে
Hello, can you say something?
Yes, now I can hear there are some sound, but I didn't clearly understood what was said.
Please, a minute, wait. বাংলা পদ্ধতি নিয়ে অ্যাপ্লাই করা হয় যেটা হচ্ছে কি আমি যখন ইউটিউব সবকিছু ছাড়া যে শুনলে একটা জায়গা থেকে ল্যাপটপ থেকে ইউটিউবে সাউন্ডটা ক্লিয়ার হয় ওই সাউন্ডের দুইটা আমি তো এই ল্যাপটপে যেটা ইউটিউব চালাই তো সাউন্ড হবে ল্যাপটপে আচ্ছা এরা কিন্তু
Says he can hear us. Follow the
Yes.
conversation. Because we haven't said much yet.
এটাতে দেখো এই স্পিকার এটা ধরবো হ্যাঁ স্পিকার এটা ধরবো হ্যাঁ
স্পিকারে ওরা লাগলে সাউন্ড
আচ্ছা আচ্ছা দেখে ফোন করছে
Can you say something?
Yes, now I can hear you loud and clear. How's my sound?
স্পিকার বক্স আছে স্পিকার বক্স আছে এটা মাইক্রো বক্স আছে আপনাদের
Hello, what is the sound like now on your end? Can you hear me?
Just keep talking. We're trying to get something.
Okay, thank you, Andrew. Nice to hear your voice.
Okay, I think we can ask some questions because he can hear us.
Yes.
So try to the microphone.
ওই ডিভাইস
Okay.
ওই ডিভাইসটা এমনিতে তো কথা বললাম অনলাইনে কথা তো শোনা যাচ্ছে
Hello, Andrew, you still there? I lost sound. Can you hear me?
Okay, we hear you. Can you speak?
Okay.
Yes,
Can
you
hear
can.
us?
Yes, I hear you loud and clear. You're back now. Thank
Okay.
you.
So just one or two just observation. One is that the here in Bangladesh actually we are started using PMB. Remember that between.
Yep.
The PMB is actually between we mix it as SBS, strident, bromine, strident. And
Yep.
clearly from your research, you can see that the epoxy bitumen is performing better than the PMB. So just can you clarify actually the epoxy bitumen will perform better than PMB? And what about the cost comparison? So what will be the which one will be the cheaper? This is one question. The other question is from your last slide. I think last slide I've seen that you have shown that the concrete pavement will more carbon emission than the flexible pavement. But did you consider the construction equipment used in the flexible pavement and the more stone used in flexible pavement? Did you consider those things during your research? Thank you.
Okay, thank you. I'll do the first question first. The polymer modified bitumen is a very good cracking resistant surface. So I think using that in Bangladesh is appropriate. Where you get additional benefits from the epoxy modified bitumen is in areas where you get significant heat buildup and where you get a lot of oxidation on your bitumen surface itself. So it gives you a little bit more benefit on the very hot spectrum of your road performance. In those circumstances, your polymer modified bitumen is not performing that well. My recommendation is that you need to use a combination of these two technologies where they are appropriate. Yo. Yes.
Dr. James, I think what we'll do is you will take the questions and then you will type the responses in the chat, and
Okay.
I'll read the responses out because we are not getting the audio output from this end.
Okay, will do. Okay, will do.
You get a full site.
Okay. Can we have the second question?
This
question that side.
this sense. Here is something.
Okay, I have actually questions. One is the compatibility of epoxy with the bitumen, whether the epoxy is checking whether any bitumen is compliant or it will get separated during the mixing. And second part is how does epoxy modified bitumen behave the viscosity, because it should be affecting the mixing process first. Third part is if there's epoxy modified bitumen in the roads, will they release microplastics to the environment? Thanks.
Did you get the question?
No, I missed that one. I didn't follow it, Andrew. Can you perhaps repeat?
Sorry, could you repeat the question?
Here is the speaker. Here is the speaker. Okay. That email.
Yes, please repeat the question.
First question was because bitumen and epoxy needs to be compatible, should there be interest in ensuring that epoxy will be properly blended with the bitumen? And the second question was because we are mixing a different viscosity material, how is this going to affect the compaction as well as coating ability? And the third question was actually because it's epoxy is a plastic, will they release microplastic to the environment?
Okay, did you get it now?
Most of it, yes.
Okay. Can you hear his voice at the back? Okay.
Is my sound
Please
better? Is
respond
my
to
sound
the
better
speaker,
now?
because now we can hear you.
Okay. For that last question, just want to remind you that using the epoxy does not change your construction processes and quality control that much. The only thing is that you have to be conscious of the time that you have before the epoxy set, and that would be in line with the time that the asphalt give you for construction before it cools down too much. So there's no special measures that you need to take account of during construction. I do recommend that you start with a few trials and make sure that you understand the construction process before you scale it up onto large-scale projects. Did I cover all the questions, Andrew?
There's a couple more. One specifically about microplastics, their release into the environment, and another one on cost comparison with the polymer modified badges.
Okay. The one about microplastics, that is, to my knowledge, not a major big deal with the epoxy. We have also recycled epoxy surfaces in New Zealand by breaking them up and then reusing it in the pavement layers. Because the epoxy set hard, it becomes a solid material. So your chances of contamination is much reduced. The epoxy costs between 3 times to 5 times more than your traditional asphalt, and I think the polymer bind bitumen is much cheaper compared to that, so it will sit somewhere between traditional asphalt mixes and your epoxy modified mixes. But cost shouldn't drive your decision. I think the decision in technology is more a question of where it's going to be appropriate and the typical problems that you want to address. Did that come through right, Andrew? Andrew, can you confirm that you heard that? Did you hear my answer?
It's the last response.
Yeah. Okay, is my sound back? Yeah, just to emphasize that the epoxy initial construction costs between 3 to 5 times traditional asphalts, but you get a similar extension of life, so the life cycle costing elements make it worthwhile. But again, I just have to stress that you need to use the epoxy asphalts where you've got specific issues with heat and with cracking. Then just on the other question, to my knowledge, I don't think there's any contamination from a microplastic perspective using your epoxies. But that's an area that we haven't specifically analyzed. The nature of epoxy is once it's set, it becomes a solid. And we have even used epoxy surfaces, recycled them, mixed them up, and then put them back into the pavement. Any more questions? Are there more questions?
Usually in my time, I think a lot here.
So you go, that's
You can ask them, go there and ask a question. That is much more easy.
Yes.
Go there.
So thank you for your nice presentation. So I have some observations. Usually a guideline, I think it should not directly prescribe any materials. Rather, we can just say that if we want to make a climate resilient pavement, it must have a rotting resistance, or it have moisture resistance against the moisture susceptibility. So, say for example, if we just want to prescribe that epoxy resin is better, but it will create some confusion because, and again, in our country so far, just we started the polymer modified bitumen. Again, the polymer is there are various kinds of polymer. So we can select so any material based on the performance criteria. Say if you so we can set the we can prescribe the performance criteria rather any specific material, I think, because say the epoxy, we are not yet familiar. Our construction technology is not yet fully familiarized with the polymer modified bitumen. So maybe the epoxy, it is also very same that our construction technology and practices is not so familiar. And again, if we just invest so many capital for just building the surface layer, so our it will affect the total budget. So yes. Why not in a guide like overseas road note, we just prescribe that yes, if we want to make a climate resilient pavement, the criteria should be it should have rotting resistance like this. It should have resistance against the moisture susceptibility. It would have something. It must be durable. So such criteria, I think it will be more expected. So that is my opinion.
Okay. Thank you. Those are valid comments. I just want to stress that the epoxy modified bitumen is not a brand name. It is like polymer modified bitumen. You get different suppliers around the world that supply it. I do think, though, that given the challenges in certain countries, the road note had to include this technology in particular. And I think over time, as your confidence grow with construction of alternative bitumen mixes, you can start trialing the technology. And but in terms of the cost challenges that you have mentioned, you're absolutely right. I think that all countries struggle with that one and that's why you've got to use expensive technologies in a very selective manner, that you don't then consume your entire budget and can't do rehabilitation on the rest of your network. Thank you for those comments. They're absolutely valid.
So yes, Anna.
His name is Thank you, Mr. Henning, for your nice presentation. Actually, I am concerned about what my previous speaker was saying, that currently we are just started to use the PMB, and we have a research where a various amount of SBS was used for the PMB. But in one experiment, you have shown that you have used 4% PMB, 25% epoxy, and 100% epoxy. But you haven't, I think it might be more useful if you have shown a PMB with a lot more like their structure, like what percentages are there in that PMB, and also there should be a life cycle assessment of both PMB and epoxy. And another thing is that in PMB, we are actually, as we have just started to use the PMB, we are worried or we are somewhat concerned about the rehabilitation and maintenance of that PMB. So is there any addition of this rehabilitation and maintenance of this flexible pavement if we use the epoxy? It might be included in the note. Thank you. Is it audible?
Thank you very
response.
much. Thank you very much for that response and also the questions. In relation to your comments on the experimental results that was done, you're absolutely correct, and I agree with you. I think the OECD research study has actually tested a wider range of other additives in comparison to epoxy bitumen, so that is available in literature. I'm also very excited to hear about your progress made with using PNB in Bangladesh. I think that you are going to get the benefits from using PNB on your network, because it does help with a bit of more crack resistance in your surfaces, and by nature will give you a more resilient surface. So that is good. Please keep on and keep on doing that development. That is good work. There's also sufficient literature available that suggests that the recycling of asphalts that had previously using a PNB binder in it can be recycled, and there's some good literature that documents that in a little bit more detail. Personally, I have not done any research, extensive research on PNB, but I know some of my other colleagues around the world have done quite a bit of research on the recycling of PNB asphalt. So yes, now please, this presentation that I gave you today is just yet give you another technology to consider, but your adoption and use of PNB should continue, and I encourage you to do so. Thank you.
Okay, thank you very much for your very good presentation. And resilience and climate adaptation is the biggest concern of this day. That's good thing. And as you have been updating this document, so it will be able to address the current issues that is more expected, and the future issues will be coming, and then these notes may be needed to update it later on. The thing is, the major concern we are happening here is the modified bitumen. That's it. So it is modified by polymer, may be modified by rubber, may be modified by epoxy, whatever is the case. So that should not be the debate. It's a if we simply say that it's a modified binder, even I'm not saying it, modified binder. Okay, so different binder adding different performance, or enhancing different performance of the bitumen as well as the mix. The thing is, I appreciate that this thing has been well thought and very much integrated into these design norms. One of my colleagues said, yes, that is not a brand name, but this could be included into a guideline or not, but we should not move into some of the specific products. So hopefully it is not in there. Okay. My next point I will be covering here is the way I was saying is that design protocol should be consistent with the construction protocol. So we can put many things into the guidelines, many things into the documents, but I always think the way I will be implementing it into the site. So if I want to implement that thing into the site, then we have to develop a coherent constructions, protocol, material testing protocol as well, and the skills we need to have. As my colleague was talking about, that we are introducing polymer modified bitumen in this country, but without knowing months of it, because we are using binder, but the test protocol is still is penetration test protocol. You got my point. So the thing is, we can discuss, but I'm just talking here saying this point. It's not a question, just an observation. The thing is, your design protocol should be supported by sound test protocol. At the same time, your construction protocol, that if it is there, this problem would be resolved. But at the end of the day, it is all about modifications of binder. But the thing is, different modifier has different, strengths and weakness. If I look at a modifier on the perspective of an environmentalist, I would be going for, okay, look at this. Like for example, if I go for an emulsion, so we don't need to burn a fire. So that could be the biggest savings for fuel, at the same time very environment friendly. But its weakest part is it cannot take a heavy load. So we should not be that much subjective. Every binder or material has its own strengths and weakness. But the thing is, at which perspective we are looking at. So we don't need to debate much of it. But my request would be to, because I didn't get a chance to go through whole of your document. Hopefully it will be there for 2 years, as you have said. Over time, we will be discussing on it. But my understanding is keep these things in such a way that it is not a standalone design guideline. It should be coherent with the test protocol, construction protocol, and other elements that needs to be addressed so that we can get a resilient road at the end. That is what I wanted to say as a comments to the presentation and the discussion that we have got. Thank you very much.
Thank you. Well noted, and hopefully the guideline will satisfy your curiosity on certain things. I just want to make a comment that the road note scope did exclude significant portions on the road construction, as it is a design guide. Thank you.
We still have another question or response or comment? Okay, I think that will be all for your session. The next session